count 11 now. Okay. But I guess we still start. Should we still start or should we wait for a moment? We wait for a moment.
I think you can wait for 2-3 minutes.
Yeah. Sure. Okay, I think nevertheless, we are going to start. So, good morning everyone, day 3. Thank you again for coming and being so brave to sit through so many lectures. We didn't finish the things yesterday which I wanted to finish, but nevertheless, I think in order to keep with the schedule, we start today the big day on photocatalysis, radical chemistry, redox chemistry, and you have the handouts if you're interested in some other issues about which we talked yesterday. You can always look at this. So today, in order to talk about photochemistry, I would like to go over some principles when we deal with radicals and some general aspects which we need to consider. But nevertheless, let me see if I'm still with you or if you're still with me. So again, a few questions during the lecture. You see here a new number in order to participate. Okay, it's not working. Let me see. No. Okay. So let's see if this is still working. I had some trouble this morning with the internet in the guest house, but I think I like challenges. Yeah. Okay. And I think we discussed a lot of the problems which we have, not only in chemistry, but also in society, and where I believe indeed chemistry can make a contribution. And so I think indeed this is a good profession to choose. Passion is, I think, is a really good motivation, because if you like something, you do it well. And if you don't like something, then you will not do it for 30 years or so. So that's probably good, and make a contribution to society, I think, is also very good. Scope is pretty nice too. When I was in your age, probably a little bit before, when I finished high school, initially I wanted to do mathematics. And then I asked myself also, what will I do with mathematics? I sure you can maybe stay at a university in an academic environment, but what are the jobs in mathematics? And again, I did not find this so attractive, what the possibilities might be. And I thought chemistry would give me much more opportunities to do something which I like. Okay, so you guys are all, and most of all, you like it. That's really good, right? So, very good. So then let's talk about some extra chemistry. And so let's talk about radicals, first of all. How do we make radicals? And maybe even in your very first organic lab course you might have done during the bachelor, most likely, at least what we do in chemistry, we do, funny enough, we start with a radical reaction. What we very often do is photohalogenation of toluene. That's one of the reactions which we are running a lot. And the way we are using and we are making radicals for this is, of course, by a homolysis reaction. This is what I have shown you here on top. And the one reaction which at least we have been using in the lab is that you use chlorine and you irradiate it and you generate radicals, right? And even more easy, and I think this is actually the reaction we ran, is that you are generating bromine, and you're taking bromine, and if you irradiate this with a daylight lamp, you start making the radicals. And then also a very important reaction then these bromine radicals will do, and this is a type of process which we will see as one of the possibilities how radicals can react, is that they can abstract hydrogen atoms. And so in this scenario when we did the bromination, the bromine radical could abstract a hydrogen. So we would form a benzylic radical, and you see we have actually quite a number of hydrogens here. It could have also abstracted something here, but it abstracts the hydrogen which has the weakest bond and which generates the most stable radical. And you see, in order to access this, and I will show you tables and where you can look at this, this is a very important parameter, BDE, bond dissociation energy. And I think it makes perfect sense that if you compare this, that the weakest bond usually is the one which is most easily cleaved, right? And then in this scenario here, your radical actually can start a chain reaction. That is a process which is also a type of reaction mode which is very common. So the radical can now react with a bromine molecule again, forms the product, the brominated product, and regenerates the bromine radical which can re-enter the cycle, right? That's a typical reaction. That's probably something you've been running a lot. So the homolysis reactions are possible, and then the alternative are electron transfer reactions from reagents. And this can go either way. You can have a reagent which will give an electron to a substrate. So this is doing a reduction. And this is shown here. Again, this is not photo so far, but samarium iodide is a really, really good electron transfer reagent. Samarium in the oxidation state here +2, but all these rare earth metals really want to move to the oxidation state +3 if they have the opportunity, and so therefore the samarium can provide an electron because it really wants to get rid of the electron, so you can form such a radical anion. So here's again an important lesson to learn. Radicals can be neutral, but they also can be charged. And so here we have an anion as a radical, and in this case it is written, as you can see it here, it is written together with the coordination. Essentially this would be formally plus now to the substrate to form such a radical anion. And the other way would be oxidative things. So here we have manganese in the oxidation state +3, but manganese really wants to become +2. And then in order to do this, what it can do, it can oxidize a substrate, right? Because the manganese needs to get reduced. And one very popular, and you will see this a number of times again, very popular substrate you can use for this are these 1,3-dicarbonyl compounds, because in principle they form the enolate very easily. They have a very acidic proton, so you can write it, if you want to, you can write it as the enolate, as the negatively charged here, and you see in my drawing here on the right, I have coordinated the manganese already to this. But now if this enolate gets oxidized, so if this loses an electron, then it forms a radical as a starting point. And in the electron which is loses, it gives to the manganese 3 and then becomes manganese 2. Right? And so there are some metals who do this 1-electron steps. Many metals you know which do the 2-electron chemistry. Think about palladium catalyzed cross-coupling. There we typically see palladium 0, palladium 2, right? This is the alternative. If we have, let's say, an aryl halide, we react it with palladium 2, whereas with palladium 0, we form such aryl palladium species, and so this is doing 2-electron steps. So some metals like to do 1-electron transitions, some electrons might want to do 2-electron transitions, and you probably can always think about this and deduce it why that is. I could ask you why is samarium wants to go from +2 to +3, why does manganese wants to go from +3 to +2? So this is now heavily inorganic, right? Now you need to know something about the electron configuration, but do you know why that is? Why samarium and all the rare earth metals really want to be in the oxidation state +3? And why is manganese so eager to be in the oxidation state +2? There must be a reason for this. I see, you could write, I'm not an inorganic chemist, why should I care? But I think it's useful to just once recall half-filled configuration. That's a pretty good term, right? That is pretty good. F7 and D5. So it looks like you know your inorganic chemistry here very well, right? So indeed, it's the stable configurations. If you just go back one, let's go very quick. So manganese has the configuration D5, And indeed, this is what it wants to become: half-filled d shell. So each the d orbital is filled. And all the rare earth metals, that's actually really interesting. They have a configuration 6s2, 5d1, and then whatever is in the f, whatever else they bring which is filled in the f orbitals. And so, in order to have a stable configuration, if they lose the electrons from the most outer shells, so that's the 6s2 and the 5d1 one, this is most easily given away. And then the f electrons, they are much closer. Again, they are there in the fourth period. They do not get not removed so easily. But the 2s2, the 2-1 and the 6 orbital and the 1 electron in the 5d orbital, this is removed very, very easily. And that's true for all the rare earth metals. There are very few exceptions, but that is why you typically find +3 as the oxidation state. Okay, so very good. So we are good about this. And I will tell you also that other metals can do this, and again, which you know very well, which have oxidation states which are stable, which only differ by one oxidation state. So copper, for example, is stable in the oxidation states +2 and +1, and I will show you how you can utilize this when you start with the copper 2 complex, that by irradiation you very easily can dissociate one ligand, dissociating the bond here in the middle. And you see this would be another way to produce a chlorine radical you can do chemistry with. And now if you think about this, why do we do this these days so much photoredox catalysis? Why do we use metal salts? Think about this. If you do the chlorination I showed you in the beginning, if you do this with chlorine gas, that is much less attractive in the way you want to handle it than if you could use a metal salt, right? So that's also one of the motivations. And this type of reaction mode, this dissociation from homolytic dissociation from a metal complex, this is not just limited to halides. You can do this. I showed you on the previous slide. We looked already at the malonates. You can do this with azides. You can do this actually with quite a number of more compounds. Then one thing which is also important, which generates radicals, are you can do this by sensitization, and especially carbonyl groups are very good in doing this. So if you excite a carbonyl group, you bring it in the excited state, and the excited state, the triplet state, you can represent as such an diradical. And again, this diradical might do hydrogen atom abstraction very, very efficiently. It will again abstract the hydrogen here, and it will abstract it in a way that you form the OH bond, and you see now what stays behind is you have a very stable radical. So that's why benzophenone is so good for doing this, because it's a resonance stabilized radical, and then you can have your starting radical which you get from your hydrogen compound, and you can use it for chemistry. And here I show you, and that also shows you that photochemistry, of course, is nothing new. That you see here is an example from the 70s where they already used this principle. And it's amazing that a lot of these type of reactions are being rediscovered, even rediscovered in the same way. Using benzophenone nowadays, very, very popular because it's cheap. 350 nanometers, you can now irradiate with LEDs. So you are able to do this in a very convenient way. And so again, if you look at this here, they did a reaction with methanol. Of course, that's again very interesting, very convenient to use even as a solvent. And you see again, you have two possibilities for hydrogen abstraction here, because I have two types of hydrogens which I could abstract from this diradical. And you can see here it's the blue one which gets abstracted. So we're making we're making this one here, and then this is actually undergoing a conjugate addition. This radical which we are forming will add to this alpha-beta enone system, and we need to talk about these type of reactions and why this radical actually wants to do this, and other radicals will not add to alpha-beta unsaturated carbonyl systems. We need to think about this. And so again, what is the parameter? Why is the blue hydrogen abstracted? Why is not the red one abstracted? Think about this. If you would use a strong base, you would abstract the red one, right? Because you would make the anion, the most acidic proton would be the one which is on the oxygen. But you can see in a radical regime, that might not be, this is not analogous. I could ask you this again. So what is the reason? Why is, if you do this with methanol, why do you abstract the hydrogen from the carbon and not from the oxygen? Right? And I think this is an answer where you can give more than one. You see these multiple choice ones are always in this way. Okay. Radical is stabilized by the donating effect of the lone pairs. That's a good answer, and that's a correct answer, but it has an interesting thing to consider. I show this to you. I cannot write on the slides where the questions are, but I want to point something out. That's why I posed this question. CH bond is weaker than the OH bond. Absolutely. Again, you need to look at the bond dissociation energies, and that's all tabulated. And indeed, that bond is weaker, and it might be a consequence because the radical is stabilized by this donating effect of the lone pairs from the oxygen. CH bond is easier to access, would not be obvious to me. That's sterically more easily accessible. Indeed, it is statistically favored, and that is something also you need to take always into account if you look at radical reactions. The bond dissociation energy is important, but very often the bond dissociation energies are similar, and then you need also to take into account that we talked about early transition states, that the radical which is doing the hydrogen abstraction might have enough power to abstract either of them, and then it simply becomes a statistical matter to from which type of hydrogens you have more. This idea of stabilization through the lone pairs of the oxygen. So let me point out again something which is of course important to consider. So first of all, a radical is a radical is an electron deficient species, right? Because it has only 7 electrons. And you know, everything in the second period, the road to happiness is 8 electrons, right? The octet rule. So by default, any type of donor should stabilize this radical. But now if you think about this, if you write this radical, and that's exactly what you said, the lone pairs might be able to donate here. But the interesting thing is you cannot really draw a resonance structure, right? It is there. The lone pairs can locate electron or distribute electron density to the deficient center. But the one thing you need to accept is you cannot really draw a resonance structure here, like we do normally when we talk about resonance stabilization. That is also known in other contexts. For example, if you take hydrogen peroxide. Hydrogen peroxide is a much stronger nucleophile than water. And again, the reason that it is it was always said that the neighboring oxygen group is a donor, and it can donate electron density, which makes this oxygen, the other oxygen more nucleophilic. And again, you cannot really express this by a resonance structure. You cannot somehow try to move the electron pair in here, right? This is not working. This would give you wrong structures. But that effect that a neighboring atom can, through its lone pairs, can act as a donating moiety, although you are not really able to express this by a resonance structure, that is really very, very real. And so this is called, here in the ionic regime, this is called the alpha heteroatom effect. And so this is not only true for hydrogen peroxide, but also if you compare ammonia with hydrazine, then again, the hydrazine is a much, much stronger nucleophile than ammonia. And in fact, if you ever work with hydrogen or with hydrazine, you need to make sure that you don't get it on the skin, because it really, much more than ammonia, it will just look for all the electrophiles you might have in terms of carbonyl groups or whatever, and just attack it. Okay, so very good. And so again, bond dissociation energies, the nice thing is that you can look it up. And there I give you here some of the tables where you can essentially find the bond dissociation energy to just about any type of CH, but also heteroatom bonds, right? And if we just look at a few, do we understand the trends? You see here the way this table is composed is that methane is taking as a benchmark. So we are not looking at we have in the left column we have the strength. So that's about 105 kcal per mole. You see again, I'm not the only one who's preaching that calculating in kcal is a good idea. You see that other tables and so on, they also do it. And you see again the reason. You stay in that range of 1 to 100, maybe a little bit over 100, right? I would have much harder time to say, okay, the primary CA or the CH here in methane it has 105, and in ethane it has 101. I grab this. But if I would have to say in methane it's 418, and in ethane it's 402, this would be much harder for me, right? I would never be able to get a hold of these numbers, right? And you see here, it makes perfect sense, right? The methane, we have a bond strength of 105 kcal, and then if you go to ethane, we go down to 101. And you all know that the more alkyl groups you put around a carbon center, the alkyl groups are donor hyperconjugated donors, and they stabilize it. So a primary radical is more stable than the methyl radical, secondary more stable than the primary, tertiary more stable, and so on and so on. And you see this here, right? You go to here's the primary radical. Here we go to the secondary radical. You see it becomes even more stable, and then the tertiary radical. And then also, not surprising, the L radical, right? Now, with the L radical, we can actually draw resonance structures, right? This becomes more and more stable. So it makes a lot of sense, right? And we talked just about methanol, but again, note here, this is also an alcohol, but it's phenol. So there the O radical benefits from the resonance of the aromatic ring. And so you can go through this, you can look it up these days, and it gives you a very good indication, first of all, how difficult is it to abstract this. So look at this here from the sp2 type systems. Here the energy goes up. A phenyl radical, and I think all have seen this also from other reactions which you might have learned earlier. We go into one of them in just a moment. This radical has no stabilization, especially not from the adjacent pi system, right? Because the adjacent pi system is orthogonal to the radical center. So if I have the pi system here, and then my radical will be an sp2 orbital, so there's no stabilization, and you can see this actually brings up the energy. it makes it harder to abstract. So that's a very good type of source you can use. And I believe there's even now a website. I think a Japanese group has set up a website. You don't even need to look at that publication. You can go to the website. I think you need to do a registration, but it's free. And then you can just search for any type of bond dissociation energy. And also equally, we will talk about oxidation and reduction potentials. And the good thing is also you can find this all in the literature. So you can find how strong or weak is a bond, and then you can find how easy or how difficult it is to oxidize or reduce the substrate as an alternative. Okay. So then also very important, we already saw this, the atom transfer type reactions to generate a radical, and we have seen already hydrogen atom transfer as an example, but it's not the only one. And so it can be, here you see this radical here will abstract any type of, or it can this is not specified, can abstract an X. And so most of the reactions which we know about is that we either do hydrogen atom transfer, but also very, very popular now, and it's actually, again, funny because that was known for a long time, is that you can also abstract halogens. And you can wonder, so why is it abstracting, when is it abstracting a halogen, when is it abstracting a hydrogen? Is that only true? I'm not sure, let me see, do I have a, yeah. What determines if it is abstracting? Now you have a radical, and let's say you have something like chloroform or so. What is the determining factor now? What you should abstract? Should you abstract the hydrogen? Should you abstract the chlorine atom? So let me ask you this: what is important now to consider? Or maybe it's no selectivity at all. All right, so let me bring this. So again, as I say, what is it if you have an unsymmetrical substrate where you could abstract a halogen or where you could abstract a hydrogen, and you have a radical, which one will it abstract? What is important here? Okay, very good. So obviously, the bond strength, of course, will be playing a role from the molecule where you abstract the atom. If that would be the only case, we would probably not be able to abstract selectively a chlorine against the hydrogen, because the carbon-chlorine bond is always stronger than the carbon-hydrogen bond. And we would not abstract selectively to abstract the hydrogen in the presence of a bromine, because the CH bond is always stronger than the carbon-bromine bond, right? But this is, of course, playing a role. But equally important is the bond you are forming, right? So we are not only cleaving a bond here, but at the same time we are forming a bond. And that can also be very different. And one of the reagents which were known for a long time is that you can generate from tributyl tinhydride with a radical starter. Typically people use AIBN and light. You can generate tributyl tin radicals. And these tributyl tin radicals, they will go after halogens, especially bromines. They will not go after the hydrogens, because the tin halide bond is such a strong bond, right? So if you have any type of, I don't know, let's say halide here or bromine, doesn't really matter so much, you will form you will abstract the halogen because the tin halogen bond is really the driving force here. And so that has been known for a very long time in doing this. And again, probably one of the reasons we are using other reagents now. Tributyl tin hydride is a great reagent to do this, but it's organotin, right? And organotin is one of the types of compounds you want to avoid. Also, whenever you should work in your lab with tin compounds and which has organic groups on there, you really need to be careful, right? Compounds, as long as they are kind of ionic, so for example, tributyl tin chloride or tributyl tin oxide, that is, this is essentially, so you can draw it like this if you want to. This is still okay because it's ionic, it cannot pass the blood-brain barrier so easily. But there are some really nasty compounds. Tetramethyl tin, for example. This is a compound we will never touch in our lab because tetramethyl tin, it's like moth powder. If you put it on the bench, you come back 5 minutes later, it's gone because it's subliming so easily. But if you ingest it somehow, it can cross the blood-brain barrier and goes into your brain. And that's really very, 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 very problematic. And so, for example, with ships, anti-fouling, they actually paint the ships, the bodies of the ships, with tributyl tin oxide as an anti-fouling component. But that is heavily debated because the tributyl tin oxide might be okay, but bacteria might hit it and they might convert it into these alkylated tin compounds. And then the fish eat it and then the humans eat it. So tin compounds, really very, very problematic. And that is simply the reason why for these halogen abstraction type reactions, tributyl tin hydride typically works great, but it's a very undesirable reagent. One thing very important is, and you will see this a lot, this is something which typically works very well, the radical addition to alkenes. That is again an old reaction. Think about this is how we polymerize alkenes, right? By doing a radical polymerization of the alkenes, right? It makes sense that this goes in the forward direction because typically if this is a carbon-centered radical here, you form a new carbon-carbon bond here, and you are dissolving the pi bond, right? Something we talked about this a lot. If you compare bond strengths, exchanging a pi bond for a sigma bond, usually this should be thermodynamically favored. But you can also see here, I already wrote the reversed arrow. That's not always the case because the bond strengths in this case might be one issue, but very often these type of reactions are reversible. And so I could ask this to you again, and I already gave you one idea why this is, but why can it be reversible? What could be the other factors? We just already talked about bond strengths. Okay. So I think it's all good answers. The one which is probably not such a good answer is this, what we just discussed, right? Trading a pi bond for a sigma bond, that is always thermodynamically favored. That's not unfavored, right? Because the pi bond, CC pi bond, maybe 80, 85, CC single bond 95 or so, so there's going up. But indeed, one of the very important issues is that the resulting radical might be less stable than your starting radical. If you think about this here, let's say we have something like a benzyl radical, which obviously is highly resonance stabilized. And now we're adding this to ethylene. And so now we're forming this primary radical, right? And the primary radical is not as stable as the benzylic radical. And so that might then cause simply that the reaction goes back very rapidly. Entropy, again, very important. In this radical addition, we go from 2 compounds to 1 compound. So it's also entropically, in general, favored to do the back type reaction. Release of ring strain can also be very important. And that's something people have used a lot these days. So if you have like a small ring, right, if that ring, if this ring, lost my microphone. If you would open up this ring here to form something like this radical here, then again this might have a very strong driving force and to go in this way. So there are a number of ways that this can be done. And then also kind of interesting is you can do substitution reactions in the very same way as you do nucleophilic substitutions. You just need to have a reasonable leaving group here if you attack this and do the substitution. And then this has to be a good leaving group. And in an SN2 reaction, usually you have a stabilized anion as a leaving group. And here you have to have some kind of a stabilized radical or so as a leaving group as well. And so I think we will also see this. In principle, dimerizations is another way what radicals can do. That is not very favorable, right? Because radical concentrations are small and the radicals are very reactive. So before 2 of them meet each other, they find some other partner to react with. And so therefore, usually if you have such radical dimerizations, it's most of the time it's a nuisance. There are exceptions to this as well. Okay. And then one thing which is also, especially in the context of photocatalysis, very important is that radicals might react with the metal catalyst itself. And that is, I think, a relatively interesting concept. I show you I show you 4 reaction modes here. We will see examples for this later on, so I will not go into all of them. But the one important issue to realize is we just said that 2 radicals finding each other is usually not favorable. But that is because the 2 radicals are unstable in itself. But many metal complexes are radicals. And so, for example, a simple compound where you, of course, know that it is a very stable compound is, for example, copper-2 complexes, copper-2 chloride. This has a electron configuration as D9, and as such, it is a radical, but it is a so-called persistent radical. And it is extremely effective to trap transient radicals. So any type of radical, and you have a copper-2 center here, will very nicely trap this and form such a copper-3 type of intermediate. And then these copper-3 intermediates typically are unstable, so if this is doing a reductive elimination, you can do the coupling between 2 of the ligands which are now coordinated to the copper and bring it back to copper-1 in this case, right? That's a typical reductive elimination you might have been encountered with palladium cross-coupling chemistry as well. So that's an important thing to realize, that the metal complexes itself can act as radical centers. And that also quite important is the metals, of course, can coordinate substrates. And so the radicals can react with the substrates which are coordinated to the metal compounds. And when we talked about the sustainable chemistry, we have seen the Ziegler-Natta polymerization. This was exactly a case where something like this might play a role, that reactions with a ligand in the metal vicinity occur. Okay, we talked about already that radicals are go through early transition states. So you have seen that example before, where I showed you that if you have an ionic reaction, that typically selectivities are better than when you do the radical, and this is simply because radicals are early stage transition states, so they don't really see so much of the stereo information of a substrate, and ionic reactions, late transition states, they feel this much better, and we have seen that example before. So here's an interesting example, which I like very much. Again, you can see this was published in 2009. Let's see if we can understand it. So what they accomplished here is that they were oxidizing a carboxylic acid, carboxylate. Similar what we've seen with the malonate anion, which I showed you. You can also very nicely oxidize carboxylic acid. And the type of photocatalyst they have been using here is they have been using these dicyanoanthracenes in combination with the phenanthroline. And so what this does is the dicyanobenzene, you can see it has electron withdrawing groups, so that easily accepts an electron. And this is exactly the electron which comes from the carboxylate. And the phenanthroline you have here is just a mediator because the dicyanoanthracene is not absorbing light. You can see anyhow here they have been using quite harsh UV light. The phenanthroline can do this, and then the phenanthroline can activate the dicyanoanthracene, and this will then ultimately oxidize the carboxylic acid. And so with this, you're getting a radical. And what these people have done here is simply they have taken the radical and then added it to a number of alkenes here, and you see here are always the alkenes, so you see here what they have been doing. But the reason I show this to you is I think that this transformation I have in this box here, this is really exciting, because look what they are doing is they're making a pretty large ring. And large rings, we all know, entropically it's not really favored, and so therefore usually yields are not very good. But look at the yield here, 83%. That's pretty impressive for making such a macro cycle. And again, and let me see, do I have a question? So why does it work so well? Right? Why in order to make these type of reactions, why is that doing this? And I think you're all with me, right? That indeed probably one of the reasons this might be, again, this is the answer most of you guys like, it's an early transition state. Indeed, the centers do not have to come so close in order to make the bonds. They can be much further away. If you would do the same thing in an ionic regime, you would have a much harder time in order to do this. And it is probably not a favorable ring size. All these medium-sized rings are not really good. Favorable conformation for the cyclization, that is clearly important, but probably light will not be able to induce this. There are ways to do this. For example, in many cyclizations, if you think about biocatalysis, occur in enzymes, and their enzymes fold molecules in order to have them in the right conformation for cyclization. So this might be a good strategy to have something which might structurize, order the type of substrates you do, but I don't think that light can do this. One thing which is being done, which becomes very popular here, are solvents like hexafluoroisopropanol. This is an very interesting solvent, because it's on the one hand, it's very unpolar with these trifluoromethyl groups, and on the other hand, it's an alcohol. And it's known that this solvent in itself, it's not like it tumbles randomly in the solution, but the solvent itself is structured. And there's good evidence for this, that if you have substrate in there, that it will structure them in preferred conformations. And for example, also inducing a folded conformation because it wants to avoid the unpolar or polar rests. So that might be a strategy. And think about this, it's also interesting because normally, probably if you would have been asked, how can I make this molecule, you would probably think about it as esterification, right? The carboxylic acid coming together with an alcohol. That is a reaction which is done very often in macrolactonizations, but it's a very difficult reaction. You have to run it under highly dilute conditions. Usually the yields are not very good. And so here, I think it's a pretty impressive alternative that you can do it by radical cyclization and actually really good yields. Okay. Let me see. So we talked already about these persistent radicals, and there is something which is known as the persistent radical effect. And what that tells you is that if you have two transient radicals, two unstable radicals, they will not find each other because this concentration is too low and they will not do this. If you have two persistent radicals, they will also not react with each other. It's kind of counterintuitive, but the reason for that is that these radicals are too stable, so they would not do this, or if you were in this situation, they would simply go back to the radicals, right? So that is also not happening. But what is very good is if you combine a transient radical with a persistent radical. This is a very good combination, and anyone of you who did maybe already a photocatalysis reaction, very often in order to see if we have radicals, then we add tempo, a persistent radical, and see if we can trap the transient radical, right? That's a very good proof for radical pathways. And I also told you that besides such tempo organic radicals, which are persistent, many metal complexes are persistent as well. Okay. And we do this later. We will talk about copper catalysis in addition to alkenes a little bit later today. Here's another pretty exciting application which shows what early transition states can do for you. This is the work of Greg Fu at Caltech University in the US. And he looked a lot about this idea to react amines with halides. And that is, of course, a reaction you might say, hey, isn't that a reaction I know already? Because this looks to me like a nucleophilic substitution, right? So nothing really new here. And the way he's doing this with photocatalysis with copper. And he is forming such copper amine complexes. So this is his idea. So he has been forming such copper amine complexes of this kind. And then when he excites these copper amine complexes, you see this one here goes from copper 1 to copper 2. So it is losing an electron. And this electron is being injected into this alkyl iodide. So it's like, in a way, like a Grignard reaction, right? So if you have the electron here, if you inject the electron, you're making the radical and the iodide ion. And then he showed that this radical now actually can react with the bound amine, which is bound here to the copper. It can do a substitution and put the amino substituent onto your carbon-centered radical. And so he showed now that you can do a nucleophilic substitution in a way to do by a radical pathway rather than by the typical ionic pathway. You might say, why is that important? Isn't that a reaction I know? And you see, he got this published in a really good journal. And I think this was probably not even his first publication. I think the first one he had was even in Nature or so. So why is that so special? Nucleophilic substitutions, this is something we know from first year organic chemistry. So why is it so special to run a radical reaction, run the same reaction by a radical pathway? It's just another pathway, right? How do you get this published in Science? Or JACS, or whatever. I can show you the reactions again. So see, you can also see some of the examples. And let me see here also what examples he has. No answers here so far. Why is this? You're all happy. You go to Greg Fu and say, you know, Greg, this is already in my textbook. You don't need this. He's a very nice guy. He's about my age and really is doing fantastic chemistry in this. Reaction occurs at a sterically hindered center. That's a pretty good answer here. So let's not drag this too long. Look at what he can be doing. He can, for example, do the nucleophilic substitution on this substrate. This is a notoriously difficult substrate to do any type of nucleophilic substitution, because this iodine here, this is in a so-called neopentyl position. Neopentyl is always the case when you have a tertiary center next to your carbon where you want to do the nucleophilic substitution. And so that is very hard, because that is sterically more hindered than a tertiary alkyl halide. That's the most steric hindrance. And you know, with an SN2 reaction, you have to do a backside attack, right? And so this is not possible, because this group will block this. If you go to Chem3D and you draw such a neopentyl halide, you will see that the T-butyl group is completely blocking the center. But on the other hand, we always have a possibility, if you cannot do SN2, we can do SN1, right? Going through the cation. But this is also very hard on a neopentyl substrate, because if you go through the SN1 pathway, you're making the primary carbocation, and that is again not working. That's what we learn, right? We learn SN1 reactions never on primary alkyl halides, SN2 reactions never on tertiary alkyl halides, or never on neopentyl type halides. But going through the radical pathway, now suddenly, and you can see in very decent yields, you can do it. And Greg Fu showed that you need the copper for this, you need the irradiation, but then it even works at minus 10 degrees. If you do it without the copper, and so just try a normal nucleophilic substitution under ionic regime, even at 100 degrees, there's no reaction. So that's very, very good, right? That's pretty cool. And so that is why he got this. Let's talk about the nature of radicals really quick. So radicals are, what are they? They are really electrophiles. They are nucleophiles. Maybe it depends. Okay, so we have a pretty good majority. Some of you still debate if it might just be an electrophile, okay? And indeed, it's a little bit counterintuitive, but it depends. In the first round, what we said earlier, we said a typical radical is 1 electron short of an octet, right? So it should be electron deficient. And as such, it should be an electrophile. But interestingly enough, it has been shown that depending on the substituents you have, if you have donor substituents, they react like a nucleophile. If you have acceptor substituents, they react like an electrophile. And there was a very nice, again, it's tabulated, very nice publication in 2007, which gave you a scale of the philicity of radicals. And you can see here, not surprisingly, the most strong electrophile of a radical, electrophilic radical, is a fluorine radical. But then a very good nucleophile is indeed the radical. Oh, let me draw this here. The radical you get from isopropanol, because this benefits from the donating substituent of the oxygen and also from the alkyl groups, right? And so that makes radicals in their reactivity very different, because nucleophilic radicals will react with electrophilic substrates, but not with nucleophilic substrates. And the same thing is true in the other way around. Electrophilic substrates will react with electrophilic radicals will react with nucleophilic substrates, but not the other way around. I show you a few examples for this. Let's look at this here. And people have measured the kinetics. So let me switch back to the pointer. So look at this here. They looked at the cyclohexyl radical. The cyclohexyl radical you would typically consider to be nucleophilic, because it has all these alkyl groups around this. It's a secondary radical. And they compared the relative rates, addition to these acrylates, and independence and they varied this group X here. And now look what happens. They start with the hydrogen, and then the hydrogen has a relative free rate of 1. And then they have put a methyl group here, and you see it goes down by a factor of 100. Now that might be, if you do this, and if you would have published this in a paper, a reviewer might say, hey, but wait a minute. Maybe it's not electronics, maybe it's sterics, right? Because you put on the big methyl group here. So this alone is maybe a little bit weak evidence. But look what happens here. Now you add a chlorine. The chlorine makes this even more electron deficient and also, in a way, sterically more bulky. Not as much as a methyl group would do, but still it's sterically more bulky than the hydrogen would be. Now you see the reaction rate goes up by a factor of 10. You put an even better acceptor, which can do through the mesomeric effect, can do this, another ester group, gets sterically more bulky, but electron more deficient, and you see rate goes up. Cyano group, now maybe the steric factor comes into place. I would consider a cyano group ballpark the same good acceptor like an ester group, but it's smaller, right? And you see the reaction rate goes up. So very importantly, indeed, that this is the case. And now they also did a very good control here. They now took the same alkene, a good acceptor alkene, and now they varied the radical which would add, and they varied it from a primary to a secondary to a tertiary radical. And you can see again, so it becomes more and more nucleophilic because you have more and more alkyl groups around this. You could argue that for steric reasons it should react slower. But you see what is happening. The reaction rate, not by so much, but overall, if you go from ethyl to T-butyl, it's about a factor of 20. You go up in the reaction rate, although you make it sterically more demanding. And that simply shows you that the more nucleophilic radical reacts better and better with your electrophilic alkene. And they, I think, did it, they also, of course, looked at steric effects, and steric effects are very important. You see here they varied the group X, again with the cyclohexyl radical. And you can see here you really have a steric effect where you go with a methyl group and then T-butyl group, make it harder and harder. So don't lose the steric aspect out of this. And then it can be done in the other way around. So you say we started here with a nucleophilic radical, The malonate radical, having 2 withdrawing ester groups on there, this is an electrophilic radical. And here they added this to some kind of a styrenes. And you see here, if you have this styrene, which has an electron deficient substituent on there, so electron deficient radical should not react so well with an electrodeficient alkene. And then you see here indeed, so this is with an ester group, this has a relative rate of 1. But if you make an enamine out of this with this morpholino substituent, you see the reaction rate goes up by about a factor of 20. And so that is again shown you, I think, quite impressively what is going on here. Okay, so again, keep that concept, nucleophilic and electrophilic radicals, and then in turn they need the right reaction partner. So if you try to react an electrophilic radical with an electron deficient substrate like an alkene, you might have not success because you simply have chosen the wrong coupling partner. This is what is called polarity match. Okay, then we talk, you can do with radicals also, you can do cyclizations, and I'll show you examples for this in a moment. Let's recall Baldwin ring closure rules. I don't know if you have ever encountered this, and I have a spelling mistake there, 5-exotric and smaller it should be. So if you think about radical cyclizations, which one is not favorable? And that's good to remember because it's actually only a few which are not really good. Okay? So the top answer is that the 5-endotric reaction is not very good. This is indeed the one type of reaction I might be able to draw it out. We look now at some cyclizations, but let me just draw it here out for you. If you don't remember, the Baldwin classified the ring closing reactions by the ring size you do. He defined this by endo or exo, and this is when you do the ring closure, you need to look which bond is breaking. Is the bond breaking inside the ring? Then it's an endocyclization. If it is outside the ring, it's an exocyclization. And then he specified the center. A trigonal center is an sp2, a digonal center is an sp, a tetragonal center is an sp3. Right? And so he concluded, if you look at this, so if we have a radical cyclization, he concluded in his landmark paper, and he hasn't done a single experiment to this paper, and up to today is the most cited paper from a publication from the Royal Chemical Society, and Baldwin did it on his desk. He didn't do a single experiment, he just analyzed what was already available. And so he concluded that in general, you see, this would be an exo ring closure because I'm attacking this carbon here and the bond breaks outside the ring. So he concluded that in general, exo is always better, faster than endo. But then he also concluded that the 5-endotric and smaller is not possible. And the reason for this is, you see, if this is my double bond, and if I'm here, my chain, if I want to do the endocyclization, I have to come to the end of this. But it's the sp2 center, so not only I have to go and attack this carbon, but I have to attack the pi bond, the pi orbital, and so I need to go out of the plane. So I have to reach all the way around. You see, the pi star orbital is somewhere like this. To reach all the way around, and I have to bend out of the plane. And then 5 and smaller is too small for this. But in difference, the 5-endodic, they are fine. They are absolutely okay. The reason for this is that now I have one pi bond in the plane, and so the radical can reach it. So that's very good. And so again, if you look briefly at some of these ring closures. Again, I showed you some of the reaction rates here. This is exactly what is reflected. So if you do typical ring closing reaction, here you have 5 exotrik against 6 endotrik. 6 endotrik is again possible, but you see that the 5 exotrik ring closure is faster by a factor of about 100, although you're forming the less stable radical, right? There's also a thermodynamic and kinetic element here. Thermodynamically, the cyclohexyl radical is favored. Kinetically, this one is favored, right? And then if you can check some of the other rates here. I don't want to go through this because I'm taking away your tea break here, and quite a number of radical cyclizations. One thing I would like to point out is radicals attack very well, do cyclizations with carbon-carbon double bonds. They do not do this very well with carbon-oxygen double bonds. And I could probably ask you why that is, and you would know the answer. Because the carbon-oxygen double bond is so much stronger than the carbon-carbon double bond. So the carbon-oxygen double bond really does not want to break easily. And so you see people have measured the kinetics, but the back reaction from such an O-centered radical to react back is about 1,000 times faster. That is different when you have a carbon-nitrogen double bond. So then again, the cyclization is favored because the carbon-nitrogen double bond is not as strong, and very often you can activate that further by protonation, and then you make it even weaker. So that is a couple of other things. So I could have asked you this, but I didn't do this. And there are some, oops, wait a minute, and there are some other issues in which you probably also know that this is last. I'm not asking any questions to this, but let me just show the one cyclization again here. The one thing, let me see, do I have it somewhere, to also keep in mind is, and I'm pretty sure you also all know this, if you compare, look at this, if you compare this radical cyclization and you compare the radical cyclization which has these 2 gem dimethyl groups in here, you see this is much, much faster. It's about a factor of 1,000 faster here. And this is an effect also to keep in mind. This is the so-called Thorpe-Ingold effect. And the Thorpe-Ingold effect says that if you want to do any type of cyclization and you have 2 large substituents, and typically it's methyl group, nature does it all the time. If you look at natural products, a lot of them have these gem dimethyl groups. And the reason for that is that the evolution found that these type of substrates cyclize easier. And so what happens is that these 2 groups repel each other, not by a lot, but enough. And then if they go outside, bend outside just a few degrees, then these 2 groups come closer to each other, and that makes the cyclization, makes it easier. So this is the so-called Thorpe-Ingold effect. That's also, when we talk about radical reactions and radical cyclizations, often a very good design principle. If you start and want to see if your reaction works at all, you typically take the substrates where you have the best chances to make it succeed. And so if you look for cyclizations, that is also something which might be a good design principle. I talked to someone yesterday who wanted to do a cyclization, right? And so there were issues of easy isomerizations, but also cyclization would probably go much easier if you would have such a gem dimethyl group present. Okay, so with this was just a general introduction on radicals. So now we are ready, and after the tea break, we are ready to do some look at actually some photoreactions. Okay, let's have some tea, okay?